The largest unit of the geologic timescale, it is divided into eras, periods, and epochs. Eon is a vast span of geological time lasting hundreds of millions to billions of years. Imagine trying to organize a massive photo album that spans your entire life. Just as you might sort these photos into broad categories like childhood, teenage years, and adulthood, an eon is the largest unit of the geologic timescale, further divided into eras, periods, and epochs for more detailed organization. Here, the entire photo album represents an eon. The broad categories are like eras, and specific events or years in your life are akin to periods and epochs, providing a structured way to understand and navigate long spans of time. A unit of geologic time longer than an age but shorter than a period. Epoch. An epoch is a time span in Earth's history marked by significant events and changes, like shifts in climate or the development of life forms. Imagine you're organizing your closet, trying to make sense of all your clothing items. Just like sorting clothes into categories like shirts, pants, and jackets, geologists use epochs to categorize chunks of Earth's history, which are longer than ages, like organizing by color within each clothing category, but shorter than periods, like the overall categories of clothing. In this analogy, the shirts, pants, and jackets are the periods. The different colors within each category are the epochs, and individual pieces of clothing are the ages, helping to neatly organize Earth's vast history into manageable parts. The second longest unit of geologic time, it is divided into periods. Era. An era is a span of time in Earth's history marked by significant events and changes in the planet's climate and life forms. Imagine trying to organize a massive photo album that spans multiple generations of family events. Just as you would divide the album into smaller sections for each family member's life stages or significant events, geologists divide this era, the second longest unit of geologic time, into smaller periods to make it easier to understand Earth's history. Just like each section of the album captures a specific phase or milestone in your family's story. Each period within this era encapsulates distinct geological and biological changes on Earth, helping scientists piece together the planet's vast timeline. A timeline of Earth's history based on major changes. Geologic timescale. The geologic timescale is a system of chronological dating that relates geological strata to time, used to understand Earth's history. Imagine trying to organize a huge photo album of your entire life, where each photo represents a significant event or change. This is similar to how geologists organize Earth's history into a timeline based on major changes and events that have occurred over billions of years. Just as you might categorize your photos by memorable moments like birthdays or vacations, geologists categorize Earth's history into different periods based on significant geological events, such as mass extinctions or the formation of mountain ranges, creating a structured timeline that makes sense of the planet's vast and complex past. A unit of geologic time that lasts tens of millions of years, it is longer than an epoch, but shorter than an era. Period. In science, a period is a time frame in Earth's history marked by specific geological and climatic conditions. Imagine trying to organize your family photo albums where each album represents a different stage of your life, like childhood, teenage years, and adulthood. Each album is like a geologic period. It encompasses a significant amount of time and contains many individual events or photos, but it is part of a larger collection of albums that represent your entire life, similar to an era. Just as a family photo album captures a specific, substantial phase of your life with many memorable events, analogous to epochs, a geologic period captures a broad and significant span of Earth's history, organizing it between the finer details of epochs and the grand scope of eras. The oldest rock layers are at the bottom and youngest are at the top. Law of superposition. This principle means that in undisturbed rock layers, the deeper you go, the older the rocks are. Imagine you have a pile of laundry where you keep adding your freshly washed clothes on top of the old ones. Over time, the clothes you first put at the bottom of the pile are the ones you haven't worn in a while the newer clothes are on top, ready to grab. This is similar to the law of superposition in geology, where the oldest rock layers are at the bottom of a sequence and the youngest are at the top. Just like your laundry pile, where the oldest clothes are buried underneath the newer additions, in rock formations, the oldest layers are found deeper down, with newer layers stacked above them over time. A gap in a rock layer caused by erosion or periods without sediment deposition. Unconformity. An unconformity is like a missing page in a history book of Earth's layers due to times when no new layers were added or old ones were worn away. Imagine you've been writing a diary every day, but then you take a long break and skip several weeks. This gap in your diary is similar to an unconformity in geology, where there is a missing period in the rock record due to erosion or a lack of sediment deposition. Just as your diary has missing pages that disrupt the chronological flow of your entries, an unconformity represents a missing chapter in Earth's history, where the continuous layering of sedimentary rocks is interrupted. The theory that geologic processes are the same today as they were in the past. Uniformitarianism. It is the idea that the Earth's features are shaped by continuous and consistent processes over time. Imagine you're trying to understand how a dripping faucet gradually fills a bucket with water, just as the continuous, predictable drip of the faucet fills the bucket over time. Uniformitarianism suggests that the same slow and steady geologic processes that shape the Earth today, like erosion or sediment deposition, have been at work for millions of years. The steady drip of water is analogous to these slow-moving Earth processes, both illustrating how small, consistent actions can lead to significant changes over long periods. The time it takes for half the atoms of a radioactive isotope to decay. Half-life. Half-life is the time needed for half of a sample of a radioactive substance to break down into another element. Imagine you're trying to eat a giant chocolate cake all by yourself, but you can only eat half of what's left each day. Just like how it takes you progressively longer to finish the cake because you keep having your daily consumption, a radioactive isotope takes a specific amount of time to decay half of its atoms. In this analogy, the cake represents the radioactive isotope. The act of eating represents the decay process, and the time it takes to eat half of the remaining cake each day mirrors the half-life, showing how both processes involve halving over consistent intervals. The breakdown of an unstable atomic nucleus, this releases particles and energy. Radioactive decay. It's a process where unstable atoms release energy and particles to become more stable. Imagine you're trying to clean out an overstuffed closet, where things keep falling out every time you open the door. Much like how that closet can't stay closed without releasing some items, an unstable atomic nucleus can't remain intact without releasing particles and energy. Just like those items need to fall out for the closet to become more stable, radioactive decay involves the nucleus shedding particles to become a more stable form, with the items being analogous to the particles and energy emitted during the process. Comparing the amount of radioactive and non-radioactive isotopes to determine rock age. Radiometric dating is a method used to determine the age of rocks and fossils by measuring the decay of radioactive elements within them. Imagine trying to figure out how long a candle has been burning by looking at how much wax is left compared to how much wax was there initially. This is similar to how scientists determine the age of rocks by comparing the amount of radioactive isotopes, which decay over time, to non-radioactive isotopes, which remain stable. Just as the remaining wax indicates how much of the candle has burned, the ratio of isotopes reveals how much time has passed since the rock was formed, as radioactive isotopes decay at a known rate. A fossil formed when dissolved minerals fill a mold and harden. Cast. A cast is a replica of the shape of an organism created by minerals. Imagine you're trying to bake a cake, but you run out of batter and only have a cake mold. You decide to use a different ingredient, like gelatin, to fill the mold and create a dessert in the shape of a cake. Similarly, a fossil cast is formed when minerals fill up the space of a mold left by an organism that once existed, much like how the gelatin fills up the cake mold. In both cases, the original shape, the cake or organism, is replaced by a new substance, gelatin or minerals, resulting in a replica of the original form. The change in a species over time. Evolution. Evolution is the process by which species adapt to their environment over generations through natural selection. Imagine trying to find the perfect outfit for a changing season where you constantly adjust what you wear to stay comfortable as the weather shifts. This is similar to how species change over time, adapting to their environment to survive and thrive. Just as you swap your wardrobe to better fit the weather, like trading a sweater for a t-shirt when it gets warmer, species gradually change their traits over generations to better suit their surroundings, ensuring they can continue to live successfully in a changing world. The preserved traces and remains of an organism that lived long ago. Fossil. A fossil is the hardened remains or imprint of plants or animals from the distant past, preserved in rock. Imagine walking into an old, dusty room and finding your grandmother's favorite chair with an indentation where she always sat. This chair is like a snapshot of the past, capturing a trace of her presence, much like how fossils are the preserved traces of organisms that lived long ago. Just as the indentation in the chair tells a story about your grandmother's habits and presence, fossils reveal the existence and behavior of ancient life, preserving a moment in time for us to study and understand. A fossil from an organism that existed for a short time, it is used to determine the age of other fossils. Index fossil. An index fossil helps scientists determine the age of rock layers. Imagine trying to remember the year a certain event took place by recalling a specific fashion trend that was popular at the time. Just like how that distinct fashion style can instantly pinpoint the year, an index fossil acts as a marker to determine the age of other fossils found in the same layer. The fashion trend is like the index fossil, existing for a short period but being highly recognizable, allowing us to accurately identify the time frame of other events or fossils surrounding it. A rock fossil created when a buried organism dissolves is called a mold. Mold is a type of fungus that grows in the form of multicellular filaments. Imagine losing your keys in a snowstorm and only finding their shape outlined in the snow after they melt away. This is similar to how a rock fossil mold is formed when an organism buried in sediment dissolves, leaving behind an impression. Just like the keys leave an imprint in the snow, the dissolved organism leaves a mold in the rock, capturing its shape even though the original object is gone. Any method of measuring the age of an object, like tree rings or carbon dating. Absolute dating. Absolute dating is a scientific technique used to determine the exact age of an object or event in years.
Imagine trying to determine the age of a family heirloom, such as an old photograph, by examining clues like the fashion or cars in the image. This process is similar to absolute dating, where scientists determine the age of an object by analyzing measurable characteristics, like tree rings or carbon isotopes, just as you might estimate the photograph's date by identifying the style of a dress or the model of a car. Scientists measure specific elements within an object, like the number of growth rings in a tree or the decay of carbon-14, to accurately determine its age.
A thin layer of carbon preserved as a fossil, carbon film. Carbon film is a type of fossil where the outline of an organism is left behind as a thin layer of carbon residue.
Imagine you're trying to save an important document, but all you have is a very thin, almost transparent piece of tracing paper to write on. This is similar to how a carbon film fossil is formed, where only a thin layer of carbon outlines the shape of an ancient organism. Just like the tracing paper captures the essential details of your document in a fragile and delicate form, a carbon film fossil preserves the essential details of an organism's shape by leaving behind a thin, carbon outline on a rock, maintaining its memory long after the organism itself has disappeared.
A method of comparing fossils or rocks to determine which is older. Relative dating. Relative dating is figuring out the age of fossils or rocks based on their position in layers, with deeper layers being older.
Imagine trying to organize a stack of old family photos without any dates on them. Just like sorting these photos by observing the changes in hairstyles, clothing, and the age of people in them, relative dating involves comparing the layers of fossils or rocks to determine their age order. The way you identify a younger-looking version of a relative in one photo and an older version in another is akin to how scientists use the position and characteristics of fossils within rock layers to figure out which is older, helping them piece together the history of life on Earth.
An atom of the same element with a different number of neutrons. Isotope. Isotopes are variants of the same chemical element that have differing numbers of neutrons, which can affect the element's stability.
Imagine you're trying to find your friend in a crowd, but they keep changing their outfit. This situation is similar to trying to identify isotopes of the same element, where each isotope has a different number of neutrons, much like your friend changing outfits. Just as your friend remains the same person despite changing clothes, an element remains the same element even though its isotopes have different neutron counts. The difference in clothing is like the difference in neutron numbers.
A fossil formed in soft sedimentary rock, like a footprint. Trace fossil. A trace fossil is a preserved record of the activity or behavior of ancient organisms, such as footprints, burrows, or feeding marks.
Imagine walking on a sandy beach and leaving footprints behind as you stroll. This is similar to how trace fossils are formed, when an organism leaves behind an imprint in soft sedimentary rock, like a footprint in the sand. Just as your footprints in the sand capture a moment of your journey along the beach, trace fossils capture a snapshot of an organism's activity, like walking or burrowing, preserved in the Earth's geological record.
The death of all members of a species. Extinction. Extinction is when every individual of a species has died out and that species no longer exists on Earth.
Imagine your favorite coffee shop goes out of business, and you can no longer enjoy their unique blend. This situation is similar to extinction, because just as the coffee shop disappears from your routine, a species vanishes completely from the ecosystem. In both cases, Something once available and perhaps taken for granted is no longer present, leaving a gap in your daily life or in the natural world, just as the coffee shop's closure leaves a gap in your morning ritual. The extinction of a species leaves a void in the biodiversity of our planet.